Okay, we are going to talk about finding the motion of a projectile in 2D and 3D planes. But before we actually start, we need to define the equations we'll be using. These equations are called kinematic equations and are often used to find the motion of objects in physics. Our first equation can be represented as the change in x equals velocity initial times time plus 1/2 acceleration times time squared. Our next equation can be represented as the final velocity equals our initial velocity plus acceleration times time. Our last kinematic equation can be represented as velocity final squared equals velocity initial squared plus 2 times acceleration times the change in x. We will use these kinematic equations to solve for unknown variables in the problems we are solving. We will start with 2D motion, and this can be easily represented as a parabola on the plane xz. Oftentimes, teachers and other people will represent this on the xy plane, but I personally prefer to do the xz plane as it's easier to convert for 3D motion, and I'll show you why later. The shape of the projectile's motion is simply a parabola. The highest point in the parabola is called the peak and is directly in between the two sides. The reason that it is directly in the middle is simply because the curve is parabolic. Since the curve is parabolic, if we represent this side as positive 5 meters per second going up, it simply means that on the other side it'll be negative 5 meters per second going down. In principle, all it means is that one side is equal to the negative of the other side. How hard the object is thrown or hit is called the magnitude, and oftentimes is represented as the initial velocity in problems such as these. There is then an angle, theta, between the magnitude and the x-plane, which represents the angle of elevation in both 2D and 3D motion. This relationship can also be represented as a right triangle where the hypotenuse is the magnitude and the angle is theta. This is important because it allows to find the components of VI, VIX, and VIZ simply by using trigonometry. To find VIX, we simply multiply the magnitude by the cosine of theta. VIZ is found in the same manner, but instead we use sine theta. By doing this, we get the separate components of the magnitude, which we can then use to find the change in x, which is distance, and t, which is time, as long as we are provided with the magnitude and theta. As previously stated, the curve is parabolic, and due to this, if we find the time it takes for the object to reach the ground, t, and divide this by 2, we then find the time at which the object is at its peak. To solve for other variables in your equation, when only provided initial velocity and the angle of elevation, you will need to use the kinematic equations and need to make some inferences about how the projectile motion is set up. By drawing vectors at certain points in the curve, you can still notice how they have both x and z magnitudes. At the peak, you will notice that velocity in the z direction has stopped and is now 0 meters per second. This is because gravity has slowed the ball down while traveling upwards, but has not yet caused it to speed back up. The line tangent to the top of the peak, as shown, only has horizontal components, which further emphasizes that Vz equals 0 meters per second. You can then plug it in to this kinematic equation and set velocity final equal to 0. You will already have the initial velocity of z from earlier. Acceleration is, of course, negative 9.8 meters per second squared, which is the acceleration due to gravity, and then 1/2 of t, because you're finding it at the peak. I forgot to put that when doing this demonstration. This concludes 2D motion, and we are now ready to start on 3D projectile motion. 3D motion is only slightly more difficult than 2D, as they are in a similar vein. Where we use two planes in two-dimensional motion, we simply add one more plane to get it to 3 dimensions. We are already familiar with the ZX planes, but the new plane that we have just added is the Y plane. The trajectory of a projectile in 3D space will still be parabolic, but it will originate at the origin and end up at some place on the XY plane. As before, the peak of the curve will once again be at 1/2 t. You can find the ultimate displacement from the origin to the final point of the projectile on the XY plane by drawing a line from the origin to the point and bringing it down to x. We will label the first line the change in displacement and finish the shape by reconnecting it to the origin. This forms a right triangle, and we can later use Pythagorean theorem to find the change in displacement once we have the two individual x and y measurements. We are already familiar with the angle of elevation from 2D motion. In 3D motion, it can be represented on either the ZX plane or the ZY plane. It doesn't really matter which one it's represented on, as in either plane it will be the exact same angle. It's hard to accurately depict, but the angle is roughly there on the graph. The new angle that we are working with is called phi and is along the XY plane. It is between either x or y and the horizontal trajectory of the projectile. Phi is more easily depicted as the angle between the change in displacement and x from the triangle that was formed by the x measurement and the y measurement of the trajectory of the projectile. There are equations similar to the ones that we use during 2D projectile motion to get all of the individual components of the magnitude. You set up the graph of the components in the exact same way as you did in 2D motion, except you just add the y plane this time. So you will get the initial velocities of the z, y, and x axes. The equation for initial velocity in the z direction is simply vi times the sine of theta, which you will recognize as the same equation that we used in 2D motion. That is because phi has no influence on the initial velocity in the z direction, so it's just the exact same thing. The initial velocities in the x and y direction are both different compared to the z direction. The initial velocities in both the x and y plane start off in the exact same way. Magnitude times the cosine of theta, as they are both adjacent to theta. As you remember earlier, we are measuring phi based on the measurements in the x and y direction and the displacement. So, we multiply the initial velocity in the x direction by the cosine of phi because it is adjacent, and we multiply the initial velocity in the y direction by the sine of phi because it is opposite to it. Since we are working without regard to friction or air resistance, we can simply multiply these two values by t to find the respective distances. These two values can then be used to determine the change in displacement from the origin to the point on the xy plane. The only variable that we have left to solve for is time, and we can easily do this by reusing our kinematic equations from earlier. And if you remember from earlier, at 1/2 t, which is also the peak of the curve, the velocity in the z direction is equal to 0 meters per second. This is an exact replica of the equation we did earlier for 2D motion, to find the exact same thing. We simply set 0 equal to the initial velocity in the z direction plus the acceleration due to gravity, negative 9.8 meters per second squared, times t. Once we solve for t, we multiply it by 2 to find the total time it took for the projectile to hit the ground after it was initially launched. When doing these equations, do not actually multiply t by 1/2. It is simply written that way to make it easier to understand. Solve for t normally, and then at the end of the equation, multiply it by 2 to find the full time it takes. Think about it like U substitution. You can later use the time to find the height of the projectile at its peak. This concludes the video. Thank you for watching.